Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept, and if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Welcome to class 18 of my course on physics 1, and we are now busy in studying lasers, which is the light amplification by stimulated emission of radiation. In lasers, I have already taken two classes. There you came to know what laser means. Okay, it is basically amplification of light. That means if you think in terms of photons, amplification of the number of photons. If you think in terms of intensity, the wave nature, it is the amplification of the intensity of the light wave. So ultimately, some kind of amplification going on because of a process called stimulated emission. So what I tried to do in the first video lecture, I tried to tell you what does it mean by various types of absorption and emission processes that can happen inside an atomic structure, and what is the speciality uh, of the stimulated emission as was conceived. The idea was conceived by Einstein long back in 1917. So I tried to tell you what does it mean by stimulated emission, and how stimulated emission leads to the amplification of the light. Okay, so that beautiful idea that I shared with you. Now the point is that after that, actually these are all Einsteinian view. So Einstein has got some coefficients there. They are actually telling you, they're actually guiding you, that in my second video I told you, they're actually guiding you that what is the rate of transition, which rate is more, whether spontaneous emission rate is more inside an atomic system or stimulated emission rate is more. The answer was that stimulated emission is always lesser than in normal system, lesser than the spontaneous emission. Even absorption process is also lesser than the stimulated emission process, because stimulated emission means consistently large number of atoms should be in the excited state, so which is not possible with the usual population or normal population of atoms. So I have actually ended my previous video lecture with a note that you now have to inverse everything. You have to create a inversion in population of atoms. You need more atoms to be in excited state. So how do you achieve that? Because you need that. Without that, you cannot conduct the lasing action. So the basic objective of this class is that how do you achieve that population inversion? And obviously there are various processes involved. We'll discuss them one by one. And once you know that, how do you actually now make a lasing system or lasing action in general, I should mention, I should explain. So that I shall do in this. So major objective of today's class is to talk about population inversion and ultimately the formation of an active laser system, okay, the production of laser. And at the end of the discussion, it is expected you will be able to explain how actually laser is produced, okay, the lasing action in general, okay, or how you can sustain even after production of laser, how you can sustain it. Okay, I will introduce a term called optical resonator. You'll come to know how it actually helps in the production of the continuous of lasers for a long time. Okay, so we'll learn all these things. Okay, this is the 18th lecture in a row. And again, for just for information, as I say every day, okay, these are my contacts. You can always contact me through these email IDs and phone numbers. Now, just to make a quick go through just the topics I already discussed. This is the light amplification by stimulated emission of radiation, and it's a Nobel Prize winning idea, the laser, because it is a very special kind of radiation. Unlike to normal light, okay, it is highly monochromatic lasers. It's highly coherent, okay, highly polarized. Okay, that means all electric field vibrates in a definite direction. Highly directional and highly intense. So all these are good news about the laser. Okay, so these are some more information. Okay, the highly monochromatic, divergence is very low, so highly directional and highly coherent. Okay, as you can see there, coherence is the key. Okay, and after that, these are various the concept of ground state, concept of excited state I have given. It's a law of nature that everybody wants to be in the ground state. So the idea is that these are the concept. Okay, if electron is in the lower and lowest energy state, then the atom is in ground state. And you keep this because we will talk. A medium means a lot of atoms are there. And if electron is in the high energy state, the atom is in excited state. Now, these are the system of atoms, the concept of normal population and the concept of population inversion. Normal population means more atoms in the ground state, and population inversion means the opposite. Now, today we actually focused on this video lecture is focused on talking about what is population inversion. You can realize with common sense. You need more atoms to be in excited state for continuing the stimulated emission process. Now we'll try to achieve that. How do you achieve that? That story I will tell you. Okay. So these are the basic stories I already discussed. Okay, this is absorption. This is spontaneous emission. Hmm.
21 she did a background. Yeah, go good good art. That's the 21 of the sheet. At তখন লেখা ওটা ওখানে সিঁড়ি থেকে ব্যাক কাউন্ট 10 করলে হয়ে যাবে 1 অবধি 20 থেকে 21 থেকে 1 অবধি ব্যাক কাউন্ট
So this is absorption, this is spontaneous emission leading to the stimulated emission. Okay, again, if you see, you can increase the number of photons. Just to remind you that you can always increase. Okay, and ultimately all the photons are moving with same energy, same wavelength, same frequency, same phase. So ultimately you get something very good. Okay, now these are all Einstein's coefficients, which I discussed in my previous video lecture. Okay, you can see the rate of, the idea is that the rate of absorption, the rate at which the electrons are moving up from low energy state to high energy state at thermal equilibrium, that will be equal to the two emission processes, spontaneous and stimulated emission. So, and when it is compared with the energy density expressed in terms of the Planck's expression, okay, then this is the, you get an idea, okay, like this. Where B's are the Einstein B coefficient, A's are the Einstein A coefficient. Now, I actually told you these things last video lecture also, the rate of stimulated emission. If you wish to calculate, it is the rate of, it is a spontaneous stimulated by spontaneous. Okay, rate of stimulated transition with respect to the rate of spontaneous transition. If you look at that calculation, it is B21 by A21 and rho nu. Rho nu we can get from Planck's law, you put it there. So if you look at the expression, from Einstein's relation B21 by A21 is equal to, because B21 and A2 B12 are same, so it is like this much. Okay, so obviously you can see there, if you look at the expression, this is the value of the AB connection. So if I put the value of that B21 by A21 and it will get it inside, so basically I am left with 1 by exponential H2 by KT minus 1. And if you put a value of yellow colored light and at a very, even at a very high temperature of the system, atomic system, the rate of transition R1, the stimulated by spontaneous emission, is very low, 0.10, it is 10 to the power minus 6 order, which tells us stimulated emission is obviously not very high here. It is rather, it is dominated by the spontaneous emission, because the inverse is the spontaneous emission. On the contrary, if you take the ratio of the stimulated transition with absorption, you can see there it is just N2 by N1. That means that means if you need good stimulated emission, more N2 should be high. Okay. But in normal system, Kn2 is always low. In the normal excited state, electron cannot stay there for longer time. 10 to the power minus 9 seconds is the time. So the message is that if you have to, even if you have to dominate the stimulated emission, if it has to be dominant one, if the rate has to enhance, if that rate has to enhance, then what we have to do, the stimulated emission, if it has to be enhanced, then you need N2 has to be high. N2 high means you need to keep more atoms in the excited state. Question is that how do you keep? Because in normal excited state, the atoms can stay for a lifetime only for 10 to the power minus 9 seconds. So question is that how do you attain it? It can stay there for only 10 to the power minus 9 seconds. So we need some other energy state where the lifetime may be less. Sorry, lifetime may be more. Okay. Where the lifetime of the electron may be more. So that thing we have to do. How do I do it? That is a question. As I can show you, you need N2 should be larger than N1. So normal excited state is not the answer. Okay, you need to do something. So that's why we need to. But it is a high energy state compared to the ground state. And here comes in the concept that if you have to make N2 larger than N1, I need a state, energy state, excited state, which is in between the conventional excited state where lifetime is 10 to the power minus 9 seconds and the ground state lifetime is infinite. And that state is popularly called metastable state, where electron can stay 1000, the lifetime is like 10 to the power minus 5 seconds or so. So when compared to conventional excited state, if its lifetime is 10 to the power minus 9 seconds, in a metastable state, electron can stay there for 10 to the power 4 times longer. So that concept we need. We need a system where the N2 will be more, so that my stimulated emission process can sustain. Okay, so that means in normal two-level lasing system, where in an excited state electron lifetime is very less, you cannot serve our purpose. We cannot sustain the lasing action. We cannot, because it can maybe one or two steps electrons will come down, and you see very soon spontaneous emission is so dominant you cannot do anything, because it's 10 to the power plus 6 is the rate of spontaneous emission. Stimulated emission, it does not have the option to take place. Then how do you do it? You have to think over yourself, and you have to overcome, you have to dominate over the spontaneous emission. How? Then that means the normal excited state is not going to serve the purpose. You add one energy state, or you introduce one energy state, or you think about an energy state, or that means just by thinking it cannot happen. You need a medium, okay, which will support that extra energy level called metastable state, where lifetime of the electron is more, like 10 to the power minus 5 seconds. So that means if I have to go for lasing action, first condition N2 should be greater than 1, that is population inversion. And secondly, I need a metastable state kind of thing, where electron can stay for a longer time. So two conditions, by default I can say you, okay, for lasing action to sustain, and the same thing is told here. You need a system where N2 should be more than N1. That is the population inversion by default, you understand. But if you populate the excited state, nothing is going to help you. You have to populate a state where electron can stay for a longer time, because otherwise stimulated emission process is 10 to the power 6 times higher than is 10 to the power 6 times lower than the spontaneous emission. So you have to overcome that limitation. So you need an extra energy level. That is the metastable state. So two things are there. And who is going to provide the metastable state? You need a medium for that. Normal medium is not going to suffice the purpose. You need a medium which will provide you that option of metastable state. And that medium is called active medium. So I mentioned what are the necessary conditions for lasing action. Three I told you. One, you need a population inversion, because for stimulated emission to take place, you need more energy, atoms should be in excited state. Second is that you need a metastable state, because normal energy state, excited state is not going to serve your purpose. You need electrons to be in a high energy state. So then automatically the connected idea is that who is going to provide me the metastable state? Answer is that you need an active medium. So these are the basic necessities of the lasing action. You see, even 10 to the power minus 3 is also available there, okay? And obviously, for another information is that powerful source of energy, okay? Because you need more atoms should be in the excited state. So that initial absorption process has to be very profound, okay? Because that will keep the atoms in the excited state, so that you can go for population inversion. So first, very profound, lot of energy density, high energy density radiation is coming in. It is pushing the electron up in the excited state. From then they may come down to metastable state for a very large time compared to excited state. They will stay there. You reach population inversion, and this ultimately you can go for a continuous lasing action. Okay. So these are the main principles. So this is in nutshell what I talk about in terms of population inversion. Okay, N2 should be greater than N1, as you can see there. Now, how do we achieve population inversion? That the general process of creating what you mean population inversion. You have to send electron from the ground state level to the high energy state. So if you do so, that means what would happen? You are actually if you send electron from low energy state to high energy state, you are basically exciting the atom. So we are keeping more atoms from ground state to excited state. Okay, so that you can do even with normal heating also, but will it do the job, as I have asked the question? Okay, you cannot achieve population inversion just by heating. You need optical pumping. Optical pumping means you have to send external photons. It may be flash lamp discharge tube, it may be continuous lamps, it may be spark gas, it may be auxiliary laser source. Okay, that means additional laser source, maybe some other laser source you can use. That will actually send the photons, which will pump the electron, which will send enough energy to the electron to move up. This is called optical pumping. Okay. In solid state laser, we will study laser, ruby laser. This electric discharge is used. There a green light is sent inside the ruby rod actually. So that it is actually incident on the ruby rod, so that ultimately it actually ignites the electron to move from low energy level to high energy level. So initial absorption process or sending the electron from lower energy to high energy level is maybe done through optical pumping. Optical pumping means you are pumping the electron but through a light to external radiation. Another is that electrical pumping. That means in this case you do electric discharge. We will do this in case of helium neon laser. Okay, you apply electric field. Okay, so basically in presence of electric field, okay, in case of ideal gas laser, okay, what would happen is the ionization of the gases will take place. So ultimately electrons also move there from low energy to high energy levels. Another is direct conversion. It happens in diodes. Direct conversion means in a diode at the junction there will be electron hole recombination process. Okay, so by this also, if you can see there, it is written there that okay, recombination process will take place, so that will produce the initial laser. Okay, and this direct conversion of electrical energy into light energy. Okay, this is the process. Okay, at the junction, okay, you have to go for population inversion. So this is the other process. Okay, you can see there. So here I get the light by electron hole recombination at the junction. Now, so obviously, if you have done, so therefore you can create the inversion of population, that is more atoms in the excited state compared to the ground state, through pumping. Now, again from excited state, they will come down to the metastable state. Who will provide the metastable state? Where the electron lifetime is very large compared to excited state. Some 10 to the power minus 5, minus 3 second, like that, much larger. So who will provide this? An active medium will provide it. So active medium or lasing medium is therefore the necessity. Now an active medium may be a solid, like a ruby rod, like ND-YAG laser, maybe a gas or gas mixture like helium neon laser. Okay, even carbon dioxide laser is also there. It has to be a medium which will provide you those additional energy level due to the metastable state, etc., etc. Okay, so basically whatever I have been telling you, you need to achieve all these things. Okay. Now this is 3-level optical pumping, where you are sending the radiation to the X-ray state, and from there on it is coming down to the metastable state. Okay, this is 3-level. Then maybe 4th-level pumping also. You see it is moving there, and you see the lowest, that E1 and E2 are almost very close to each other. So these are variety of who is providing the energy. Obviously some active medium. Okay, you can say metastable state is also there. Okay. Now, this is what we need for laser action. Active medium is marked in orange there, you can see. So what would happen? On those YOLOs are actually excitation mechanism. That means you are doing optical pumping. Suppose you are making incidence of some light. The electrons in the, because of this, what would happen? I just show you with a, I try to show you. Okay, these are actually sending, these are actually making incidence of photons here. Okay, say suppose you are doing optical pumping. So in active medium, obviously these are the energy levels. So what this you are providing, that means from ground state to excited state you are sending the electrons. Okay, a lot of electrons will move from ground state to the excited state. Okay, they will move from ground state to the excited state, but they cannot stay there for a very long time because excited state lifetime is very low. So now this is your metastable state. Now in metastable state, this electron will come down to the metastable state. Here lifetime is relatively larger, okay? Actually 10 to the power 4 or 5 times larger compared to the excited state. So now electron is here in this energy state. So what would happen? Electron will come down because of the spontaneous emission. After 10 to the power minus 5 seconds, suppose it is coming down. The moment it is coming down, what is happening? One photon is coming out. Now this photon is coming because of spontaneous emission. Okay. Now this will actually activate the further activate the emission of more photons. Now how it does, let me show you directly in pen and paper. That will be more easier for you. Okay. Just give me a second. Before that, let me introduce this. Okay. Just give me a second. Okay. Suppose I've got an atomic system. Okay. I've got an atomic system like this much. Now from this energy level, I've made incidence of an external photon and moved this electron up. So this is my ground state E1. This is my excited state maybe E3. Like this much. So if I draw it in a proper picture, In normal system, what happens? If this is E1, if this is E2, so electron here from here are moving up because of the excitation. So it cannot stay there for a very long time because of the lifetime. Now, if the number of electrons per unit volume is N1, and here the number of atoms in excited state is N2, so very soon they will come down here. But this is the metastable state. Here the lifetime of the electron is very high, 10 to the power minus 5 seconds. So now what would happen? After 10 to the power minus 5 seconds, because of spontaneous emission, electron will come down here. So and radiation will come out. Okay, one photon will come out whose energy, if it is EM say, is EM minus E1. Now what this photon will do, now it is now you see your active medium will be such that, so now this is your metastable state. So what would happen? Okay, any atom, because here the atoms can stay for a long time, 10 to the power minus 5 seconds or so. So now this will be actually ignite the process of stimulated emission here. So one electron will come down from here now. If it comes down now, so you get two photons now. Okay. Now these two will ignite the process of stimulation of two more. So two more photons will now come down because this is going on. Stimulated emission is active now. So you get a lot of bunch of photons coming out of the system therefore. Okay, a lot of photons coming out. But there is in this way you can actually from, so that means from 1 to 2, 2 to 4, 4 to 8 and so on, you can just create an avalanche of photons. But you see your system that you have drawn here in front of it here, that I have drawn here, it has got no out. You see, if you look at the system, okay, it will be stopped after some time because soon this will become, you see, radiation is going out. So once it is going out, suppose it is from 4 to 8, you have just grown it up, okay? 4 to 8, suppose there are again, this 4 will cause 4 more photons to come up, 4 to 8, 8 to 16. But this process is not going to sustain for a long time. Okay, so your active medium is providing energy level. Lasing action is, you see, of stimulated emission is making the growth of the number of photons coming out. But problem is that if you think quietly, you cannot sustain this process because of common sense. Because once these radiations are out, okay, you cannot continue this for a very long time. So what you have to do here, you have to do this much. You see, again, these are your energy levels. Try to realize. This is E1, this is E2. So electrons are moving up. Now, this is metastable state. So electron is going down here. So ultimately, if it comes down here, photon is coming down. So basically, this will cause the emission of two more photons. So now, how many photons I have got? So this will cause the emission of one more photon. Sorry, I will get two more photons. Okay, one more. You get only one photon from here. Now these two. Okay, this is not there. Okay, these two will cause the emission of two more photons. So how many photons you have got? 1, 2, 3, 4. Now from 4, you see here 4 more photons will come down. So 4 plus 4, 1, 2, 3, 4, 5, 6, 7, 8. You have got 8 photons. So large number of photons are coming out of the system. So in this way, from 1 to 2, 2 to 4, 4 to 8 to 60 will grow up. But we have to keep, you see, we need this process can sustain for once. But I want to keep this system for a long time. So what is done actually, two mirrors are used here. Suppose this is one mirror and this is the other mirror. Suppose this mirror is made fully reflecting. So all the radiations going in this direction, now they will be reflected back into the system. So if 8 are going on, 8 will be reflected back. So they will now further ignite the process of stimulated emission. So now from 8 to 16, 16 to 32 as they progress along. So when they will be in this way, they will be reaching to this other mirror. So from here also they will be reflected back. So in this way, radiation will grow up. Okay, amplification will grow. Amplification in photon numbers will take place. Lot of photons will come out. Then question is that where is the output? To get the output, one of the mirror is made partially reflecting, so that when it is sufficiently intense, so ultimately some of the radiation can go out of the system and you get output of the system. Now this system, which is actually producing this an active medium placed between the two mirrors, it is called an optical resonator. So that means the fourth option that you need for laser to produce is obviously first population inversion, second metastable state, third you need a lot of high energy density radiation for optical pumping to take place, and you obviously need an active medium who will providing all those energy levels of the atoms, and also now you have to form an optical resonator, otherwise you cannot sustain. So these are the basic lasing action. So with this in mind, let me get back to the PowerPoint. If you get back to the PowerPoint, you will notice, okay, that is the active medium. You see optical pumping is taking place by the zeolos. And you see one of the mirror is fully reflecting, other one is partially reflecting, and you get an output, okay? Okay, understand? So this is called, this cavity is of course a Fabry-Perot etalon, okay, this is called. And this is the optical resonator or optical cavity, whatever you say. Okay, so what is an optical resonator? This system that I have just shown you. Okay, if you come to this picture, this is the optical resonator. Okay, so here I formed an optical resonator, which is growing the photon numbers. Okay, so in one word, actually, optical resonator is made like this way. Okay, you need an active medium who is actually providing all the energy levels. You need mirrors. In my drawing, it is 100% reflecting, and this is partially reflecting. So when the photons are coming out, if two photons are coming out, two photons will reflect back. So if four photons are coming out, four photons will reflect back. So in this way, the photon number will be growing. Okay, when it is sufficiently high, photon will be coming out of the system. This is the arrangement of optical resonator. So for lasing action, you have to form an optical resonator. Okay, and obviously which I have not drawn. This for initial ignition, you have to do optical pumping also. Optical, electric, whatever you like, but optical pumping is the popular one. You can see there. Now, based on this choice of medium and how you are getting the laser may be defined in several ways to classify this laser. One is obviously choice of medium, another is that how you are getting the laser. And classification can also be done based on the gain of the laser medium, power delivered by the laser, efficiency of the laser, and applications of the laser. But broadly, it may be divided into on the basis of choice of the medium. Laser may be solid state laser, example ruby laser, gas laser, example helium neon or carbon dioxide laser, liquid laser is also there, semiconductor means diode laser. Okay, so this is the lasing cap, and in terms of how we are producing the mode of operation, there are two classes actually: continuous mode operation and pulsed. Ruby laser will be producing pulse laser, and helium neon laser I will be discussing, it will produce continuous laser. Okay, So this is the lasing action in general. So I introduced that by the formation of optical resonating system, how we can produce laser beam. So thanks that for the time being, because next time I'll be coming with some active laser system. Okay, in your syllabus, okay, ruby laser is there, semiconductor laser is there, and helium neon laser is there. So these three lasers we'll discuss, and automatically ruby laser is solid state laser, helium neon laser is gas laser, and the other one, diode laser, is also solid state laser, but optical pumping is different. Direct conversion takes place there. So we'll discuss them in the next class, okay? Because that it will be all about classification of laser based on the medium, and automatically other classification. Who is producing continuous wave, pulse laser? It will automatically taken care of. Okay. I have already told ruby laser is a pulse laser, helium laser, neon laser is a continuous wave laser. Why I am classifying this like this? So to learn this, you have to learn the details of how the functioning of ruby laser and helium neon laser. As you can see there, this is the optical resonating system. Okay. Okay, the optical cavity, the mirrors are there. Now, if you come back to the PowerPoint, you will realize, okay, this is what I was talking about. Okay, this is the optical resonator system. Okay, the active medium is there, the mirrors are there. So actually, mirrors role is to help you in growth of the radiation. Okay, so if it is coming out, whatever with the radiation coming out, it will be fully reflected back, so that when it enters in the medium, it actually creates further growth. Okay, and ultimately when it is sufficiently high, it can go out of the system. So this is a resonating cavity. Formation of optical resonator is must for the lasing medium. Fabricated Italon is a cavity, as you could see. And as I mentioned a few minutes back, that active medium, if you have to devise a laser, obviously you have to rely on active medium. That will talk about the type of the lasing system, but this basic structure should be there. Usually those mirroring actions are created by silvering, by coating with silver, etc. Partial silver coating or full silver coating, all these things are done. Okay, so basic mandatory necessity of the laser is that you have to form an optical resonator, and in order to inside optical resonator, you need an excitation that is for optical pumping. You need the active medium, and who will be giving you those metastable state, because without at least three energy levels are needed, because only with two energy levels it is not going to sustain, as I told you. Then stimulated emission will be very less. Laser action cannot come. You need energy levels having a larger lifetime. Okay, so these are the basic necessities. Again, I repeat it. Basic necessity, you have to create population inversion. To create population inversion, you need more atoms in the excited state. So normal excited state is not going to help you. You need a metastable state. Who will provide you the metastable state? Active medium. Now in active medium also, to who you need the concept of optical pumping to create the population inversion. Again, the laser coming out of the active medium also cannot sustain for a long time. So that's why we need to frame that mirror system which will reflect back the light into the laser into the medium to create further stimulated emission and ultimately growth of the total number of photons. And ultimately, this system is called optical resonator. These are the essentialities. Now, based on the way laser is produced, actually various classifications are there. Some of the lasers are solid state laser, like some that is depending on the medium, and like solid state laser, gaseous laser, liquid laser. And depending on the way you are getting the output, continuously or pulse, there is another classification, continuous wave laser or pulse laser. And other classifications we can do also depending on its efficiency, power delivered, okay, gain of the laser, amplification of the lasers. Now we learned solid state laser, ruby laser, gas laser, carbon dioxide laser is not in your course. You'll be only learning helium laser, neon laser. You'll learn another solid state laser, the semiconductor laser I've written separately there, like diode laser, and liquid lasers are also there, which is not included in your course. So this is the basic structure of the laser. Okay. Now here I end actually, because our next turn is to talk about this individual system of lasers in detail. And as I told you, that lasers can be continuous wave or pulse. Ruby laser is an example of pulse laser system. Helium neon laser is an example of continuous wave laser system, but how they produce pulse laser, how they produce continuous laser, so these things need to be known to you. Okay, we'll discuss them in the next video lecture. Thank you.
You and me were meant to be in the great outdoors, forever free. You and me meant to be in the great outdoors, forever free. Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together, it's so beautiful. You and me, we meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell